for Health at Newcastle University, which is situated in the Population Health Sciences Institute. I had the pleasure of working with Paul from 2016 to 2019, and I still keep in very close touch with him. We worked together on the Connected Health Cities project, which kind of was a test bed for the Great North Care Record, and we learned an awful lot about regional health system interoperability, as well as data analytics at scale across multiple organisations. And it's that latter thing that we're going to touch on today with Paul's basically Paul's baby, which is called Datashield, and he'll tell you all about Datashield and how it will work. So he's a great guy to work with, and he's got a great sense of humour. So you can say anything you like to him, and I think he'll cope. With that, I'll hand over. Oh, well, if you'd like to just tell everybody your sort of medical background and everything before you start, Paul, I think that would be, helpful. But anyway, on you go.
So is that the medical background of my current respiratory tract infection, which might lead me to lose my voice in the middle? If anybody, if two reasons why you may lose me in this. First of all, my voice may become too hoarse, but I think I'll be able to deal with that because I've got quite a loud voice. And the other thing is there are some issues which nobody can understand about my Wi-Fi link here, and I may occasionally just disappear temporarily, but don't worry, it does always come back. So don't worry about that. Yeah, just to reiterate what Nick's saying. So basically, I had the great pleasure of working with Nick, as he said, between 2016 and 2019. And while I was working with him, there were these two main projects. There was Connected Health Cities, during which particularly Nick taught me a very large amount of what I currently understand now about the actual information systems in the health service. And then in parallel to that, Datashield, which is the thing that I've been working on since 2009. And that's up until recently is focused primarily on how you share information, sensitive data in settings that have largely been research settings with multiple epidemiological cohort studies. But anyway, so today I'm going to go through and explain to you about what Datashield is, but just specifically to answer the question that Nick said at the end. I did originally train in medicine. I was one of the third intake into what was then the new Leicester Medical School, and in 1977, and my brief bit of clinical training before I realised that I wasn't the right person doing the clinical work was I worked in renal medicine, but since 1988, when I finally realised that unless I was going to do medicine first full time, I shouldn't be doing it at all because I couldn't work out how to do things quickly enough. Since then, I've been working in bioinformatics, or in fact, originally biostatistics, genetic epidemiology. Okay, so let's get down to Datashield then. So this Datashield is an open source project that's currently, for the last 4 years nearly now, been led from Newcastle University in the Population Health Sciences Institute. What I'm going to do in this presentation is first of all tell you what Datashield is, and in that I'm going to explain why we need something like what I'm going to describe as Datashield, what Datashield actually is and how it works, and then a little bit of additional information about Datashield and some discussion points we might be able to discuss. The big issue that Datashield needs to deal with is the fact that if you're actually doing large-scale analysis in epidemiology or in many areas of biostatistics, what you really like to be able to use most of the time, if you can, is have access to individual level data on individuals, a group of individuals you're going to study. And as many of you will know, amongst informaticians, those are often called the microdata. So basically, we'd like to be able to work with them in contrast to the option, which is that you could work with summary data. So you could simply take data across a population, do some summary work on it, and then do analysis on those summary statistics. But you'd really like to work with the microdata, and the reason for that is really twofold. First of all, there are quite a range of analyses that you literally can only do if you work with the microdata. So it's a matter of either doing it with microdata or not being able to do it at all. And then the second reason that a lot of people know about and think is really important, but in fact actually often isn't as important as people think, which is that if you've got a whole lot of data on the level of individuals, it's generally assumed that if you then start summarizing those rather than working with the actual data, that you're going to lose statistical power. So basically you're going to be able to extract less information out of the data than you could if you worked with the individual data directly. And in fact, most of the time that's not actually true. Most summary statistics that we work with in biostatistics are what called sufficient statistics. So they actually contain most of all of the information you actually need for the analysis. And in those cases, it really doesn't matter whether you work with the summary data or with the individual level data. But the fundamental point that if you don't use the individual level data, you literally can't do a lot of analyses is the killer in terms of wanting to use the microdata. Now, we then reach what I've recently started calling the current data dilemma, which is that, so the science is best driven by the individual level data, but there are a series of reasons why we can't freely share or pull together individual level data. And the three main reasons are first of all, so in the areas of the life sciences, particularly where humans are involved, a lot of the restrictions on sharing or pooling individual level data are ethical, legal, or other governance restrictions. And these can either actually ban you from doing some analyses, or else can lead you to have to go through very prolonged application processes, which can really slow down the progress of a project. So basically, that's the first reason why we can't freely share individual level data. The second reason, which is over academia or over science as a whole, is actually probably the biggest reason, because this applies to all areas, is basically maintaining control of intellectual property or commercial assets. So for example, if you've invested a huge amount of money, university money, in developing a telescope array, and you now want to be able to share that with other people, you may not be very keen on actually having to be able to hand out the individual level data from that array, because as soon as they've got that, they're then in a position to then just go off and do stuff themselves. And so the second reason why we don't freely share microdata is, first of all, then the concept of intellectual property. So the actual intellectual work that's been built into the development of those data. And second thing is that increasingly so a lot of these also have commercial value. So this is a second reason why we don't freely throw around microdata. The third reason is going to become increasingly important. To date, this hasn't been an issue we've had to deal with in Datashield, but nevertheless it will become so at some point, which is that modern data objects, particularly, for example, visual graphic things from body scans and things like that, can have a huge physical size. And under those circumstances, you don't really want to be throwing those large data objects around from person to person. So there's a series of reasons why, although we'd like to be able to share and work with the individual level data, in practice is not as easy as we might wish it to be. So what can we do? And so in 2009, in fact, the concept of Datashield was suggested as a way to get around this. So this is a way of, could you share individual level data across from a series of sources in a way which meant that you were keeping control over the disclosure risks and the other issues I've just said, such as the intellectual property and things. So what is Datashield? So first of all, I'm going to describe it in much more detail during the talk, but Datashield is a client-server architecture that's built totally on open source freeware. The two main components of that freeware are R, which a lot of you will be used to, and we also, our R system is built into an OPAL database, which is a MongoDB database developed by a company called Abiba, who we worked with from the start. And originally they were based in Canada, but they're based in France. The idea of Datashield is that, so the first part of it is that rather than trying to share the individual level data by handing that around or putting it into a central warehouse, what we want to do is leave the data where it is in the individual studies, and we're then going to try and pipe the analysis to the data. So in effect, we're trying right from the start to adopt a federated approach to analysis. The data then will be able to sit on the local servers where they normally reside, crucially behind the firewalls where they usually live, which means that the studies that actually own those data, and this, I'll use the term studies because most of our work is based on studies, but whenever I say studies, this could also be various health service agencies and the data that they've got, so they're interchangeable. We've got all these data sitting where they normally do, behind their normal firewalls, and then the client part of the architecture is going to allow us to issue commands into the system, which then basically trigger analyses to be done in each of the data sources, and then they're going to return appropriate results from those back to the client. And as I say, I'll say that in more detail in a second. The key feature of Datashield, which allows you to do this, is that when you send the analytic commands in R to each of the data processing sources, the studies, then what they're actually going to generate is non-disclosive summary statistics, which, for example, could be means, something like a mean or standard deviation, or they could be other more sophisticated statistics, things like information matrices and score vectors. And the key feature about virtually all of these summary statistics is what I mentioned a few minutes ago about sufficient statistics. These are generally sufficient statistics, which mean they carry all the information about the analysis from these studies, even though they represent a summary of the data in the studies, and therefore we're able to do a fully efficient analysis, which allows us to really understand what's happening at the micro data level. So one of the key features, as well as being federated analysis, the other thing that we've done is to have a series of multi-layered disclosure control systems. Again, I'll say more about that soon. But the minimum bottom line is that in all cases of Datashield, even when you've got the least level of disclosure present, what it says is that the minimum bottom line is that the analyst, so if I'm sitting here doing some analysis through the client, I am unable myself to see, copy or extract any of the individual level data held in the studies. So I can analyze them in this fully efficient manner, but I cannot actually see or copy them. So this is providing a good way of enabling studies, in this case, to share data, but without having to have permission from their governance structures to actually give away their data. And the final point is that all the analytic processing and the options for disclosure control I'll tell you about are all located with the microdata, so they're held at the servers, at the studies where the data are held, and so studies maintain complete control of their own data. So just a minor point that I'll mention very briefly just before getting on to the rest of the talk is that when you've got data split across multiple sources, there are two ways they can be split. The first one is called horizontal partitioning, And this is where you've got a series of different sources, each of which hold all the variables you want, so the same set of variables, but on different individuals. So this is the typical situation that works. For example, if I'm working with 14 cohort studies, each of those cohort studies will have been set up to have all the same variables. So I've got all of those, but of course, each cohort study will have different individuals. So this is what's called horizontal partitioning. It's what happens actually in meta-analysis that I'll talk to you about a bit more later on as well. And virtually all of the work we've done today with Datashield has been about horizontal partitioning. And the reason for that is we've been so successful with that, we've never had time to move on to the more complicated issue of vertical partitioning. But it's still, the vertical partitioning is potentially of interest, and I expect that I might get questions at the end about this. Vertical partitioning is when you've got different sources, each holding different variables on the same individuals. So the situation, one of the situations where we did some development work on this was in the Outback project in Bristol, which was a cohort study in a birth cohort, was followed forward. And basically, you might well want to be able to do an analysis that takes data from the Outback study, combine it with data from primary care and data from education, and then pull all those together and do an analysis. And that clearly is a record linkage setting. And the maths of dealing with that are quite a lot more complicated. Nevertheless, that's something we could discuss later on if people were interested. All right, so now let's look at this in slightly more detail. So this is on the right-hand side here is a schema of Datashield, and I'll describe that in a second. As I mentioned, the key principles when we originally set up Datashield were that we wanted to be able to enable federated analysis so the data could stay where it actually normally lives. And we wanted to have some sort of disclosure control to prevent the risk that information was going to be passed out that you didn't want to pass out. And just to slightly, the term controlling disclosure risk is a completely arbitrary term that we use, and it's not got a formal definition. But just so you know what I'm meaning I want to control the risk that a data analyst is able, either accidentally or deliberately, to infer the identity of one or more of the individuals being analysed, and or to infer the value of key variables characterising that or those individuals. So the first point is, do we accidentally or deliberately identify people? And secondly, if we did, are we going to then try and identify things about them? So we don't want those things to be easy. We want to block those. So the initial, on the right-hand side, the initial development of Datashield was all about what's called the multi-site horizontally partitioned Datashield. So this is where we've got multiple data centers. Here on this slide here, we've got 6 being schematically represented. Basically the data, as I hinted at a few minutes ago, is horizontally partitioned. So these may each be a cohort study with the same type of data in each study, but with different individuals. Okay, so first of all, what have we got here? So around the outside of this, we can see we've got, at each study, we've got what I'm calling a data processing server. And in a later slide, I'm going to talk to you a bit more in detail about the architecture underpinning that. But for the moment, let's just say we've got a server which allows the data to be processed remotely. And in the center, we've got an analysis computer. So for example, in a number of settings, my computer here that I'm giving this talk through is often used as an analysis computer for a Datashield setup. And so sitting on the Datashield analysis computer, what I'm going to do is I'm going to send commands out that go to all, they'll go to all the studies by default, but I could choose to send to a subset of them if I wanted. But let's assume we're going to all of them. And those commands will go out to the studies and ask them to do the analysis we want them to do. And as well as then having done that analysis, we're then going to ask them to return these non-disclosive summary statistics back to the analysis computer so that the analysis computer can then interpret the results. Now, if you look here down the bottom right, I refer to the parser. Now, I've used people who used to electrical circuits will recognise this is a diode, which I realise is not actually a very good analogy. But the key issue is that what comes out from the analysis computer can be sent to the data processing servers. Going through this diode or whatever it is, what it's actually doing is, one of the things it's doing is going through a parser, and in going through that parser, only valid commands, only valid Datashield commands will be allowed to pass. And it's not only the particular commands you're allowed to send, but it's also what arguments those commands can have. So you send a command with a certain set of arguments with it, and provided the command and the attributes are allowed to be sent, that will then get to the data processing server. It will then send it'll do the analysis, create the summary statistics you want, return those, and they'll then go to the analysis computer. So in one direction, the diode only allows valid commands. In the other, it allows free flow of summary statistics, but only those that are produced by the data processing server. The dotted line around each server is showing the firewalls that are existent. And so that's basically what for about 4 years, this is what we were doing. All the original development was all about this. But after a bit, we realized that if we were investing quite a lot of money in developing a disclosure control system, then in that case, there's no reason why you can't use that on a single study. So we've then developed that for single site Datashield. And a key point about single site Datashield is this means that you can allow the disclosure control of Datashield to be applied even when you're electing, rather than to do federated analysis, you're electing to move everything into a central warehouse. So basically, Datashield can be used as a disclosure control system in either setting. So this disclosure control is obviously critical to Datashield. So how does it actually work? Basically, there's a whole series of layers to this. And the top 4 here are things that are actually fundamental, sensible things you should do on the hardware that you're running everything on. So first of all, if you're going to run Datashield, you should be running it on some sort of robust hardware. So you don't just stick it on any old poorly protected computer anyway. You want to run it on a good computer in some institution which has good systems. And secondly, as always, when you're passing information around in anything to do with health, then anything that's passing anywhere within that should be being encrypted in standard ways. So I'm taking that as read that that's going to be happening. Equally, as we all know, if you actually set up any formal analysis of health service or research data in the modern world, then you're expected to have set up formal governance arrangements. So you will have ensured that you're meeting GDPR requirements, etc. And those equally need to still be met by Datashield. So having Datashield doesn't mean you can then forget about those. You can think about them, and it will in fact make some of those governance agreements easier to obtain, but nevertheless you do still need to have them. So you need to have those 2 things. Thirdly, every time you initiate an analysis in Datashield, then all that command and the outputs produced from each of the data processing servers are all logged, and those should be logged permanently and held with each of the data processing servers, such that if something happens that we can find later on there's been some data misuse or data leak, we can then go back and try and identify when it happened, who did it, was it deliberate or whatever, and if necessary, we can set up sanctions for it. And then the 4th hardware issue is that the data processing servers are not the same thing as the main data systems that you've got that you hold your data on normally. This will become clearer in a later slide. Basically, we don't, even though we want the data processing server to be behind firewalls at your center, we don't suggest that it should be sitting actually on your main data servers, because if anything does happen, then we don't want people to burrow through from one to the other. So generally we want to keep the data processing servers separate from your main So those are the hardware, sort of hardware and governance baseline. Then in terms of the actual system itself, so first of all, the analysis is actually being done on the R systems in the data processing servers, and the key issue is that those R systems are set up so the only way they can do any analysis is via commands coming in from the OPAL server on which they sit. And the only way you can get commands into that OPAL are through this diode parser thing. And so basically, there's no way that anybody can go in and start doing other analysis that you don't want on that in those R environments. Secondly, so we've already said the parser blocks things going and you don't want. But in addition, every time we write a new R function in Datashield, we build disclosive blocks into each function. And one of those, for example, which we'll see about in a minute, is the table function. And the table function has the software that calls the table function doesn't allow if the minimum cell size in a table is less than a value that you've chosen, then it won't allow that table to be produced. So there's a whole series of, at the moment, about 10 different things that block different optional things you can do for the disclosure controls. Coming back to what I said earlier on about the minimum bottom line. The minimum bottom line is that functions like print are simply not allowed at all, because if you could do print, then theoretically you could simply just ask the Datashield to print the values of a variable and then return that. So basically we don't allow clearly disclosive things like that. But in addition, if you run functions like, for example, a generalized linear modeling function, standard generalized linear modeling function in R will produce a series of things that come out at the level of individuals, which are the residuals, which are the difference between what's observed in that individual and what was actually predicted from the model, and fitted values, which are what the model predicts that individual. If those were returned, then those will be fully disclosive. So basically our glim function in Datashield has those blocked. So basically we're very selective. So that leads to this fact that the individual level data are invisible and cannot be copied or abstracted. We've already mentioned the parser, and then the disclosure tracks are these things we built into the software that control things like minimum cell size. So I'm just going to drink. The final thing which I mentioned a bit earlier on is that all the controls on the disclosure controls are owned and held by the data processing servers themselves and their data custodians. So basically this is how the data custodians keep complete control over their own data. Then the other thing to mention at the bottom of this slide is that there's two ways. If you're trying to combine data together across all the studies, there's two ways that you can do that. First of all, you can do a full likelihood fit, which is basically you analyze the data in a way which, if you're using sufficient statistics, is exactly like taking all the data, putting it centrally in a central warehouse and analyzing it there. The second thing, and I'll show you how that works in a second. Then the second thing to say is that the other way of doing it is equivalent of a two-stage meta-analysis. So basically, the analysis computer asks each study to fit a model to completion, then return the results of that model from each study, and then pull those together in a meta-analysis. So those are the two ways we can do analyses. So let's look in slightly more detail at functions. So this is the DS, a schema of the DS summary, the DS table function, which creates contingency tables, which can be anything between 1 and 3 dimensions. So what happens is that the client, this is for a 2-dimensional table, the client sends a command that says create the 2-dimensional table for your study. Each study does that. Then return that study because that table is in itself an undisclosed summary statistic. puts those centrally, and then all you need to do for a table is to add the tables at each set for each element of the table. You add across all the studies, and the answer you get is the value across all studies. So that's the basis of this DS table. And the main disclosure issue here is the one we mentioned earlier, that if you have a cell size that's too small, it can start becoming a risk of disclosure, and therefore the contingency the disclosure controls include this option of what's the minimum cell size you'll accept. Now this now shows what happens with a more complicated analysis, an iterative model such as a generalized linear model. And the key issue here is that you start off by sending a command from the analysis computer to each of the data processing servers, which says, please fit one iteration of this GLIM, which is a regression model. And at the end of that, return the summary statistics, which are sufficient statistics for that, which are called a score vector and information matrix. And just to see what I mean by those, so if this is a model, in a model with 4 regression coefficients in it, the score vector will just be a vector of length 4, and the information matrix will be a 4x4 matrix. And no matter how many, or even if there's 5 million observations in the data set, the score vector information matrix will still be these sizes. So these are fundamentally non-disclosive. These then get returned back through the diode to the client, the analysis computer. And all that does is it sums the score vectors, sums the information matrices, and then it calculates the sum of the score vectors over the sum of the information matrices, adds those to the current value that you were previously guessing on what the coefficient vector was, and this creates the updated coefficient vector. And this way of doing this is in fact exactly what is happening mathematically when you fit a regression model normally in any regression program. So you're precisely replicating what happens normally. You then take this updated coefficient vector, send it back out to the servers, say now do another iteration of that of the generalized linear model, calculate the score vectors information matrices again, return them, and keep going until the model is converged, the results are consistent from one iteration to the next, and that is then the answer that you need to get. And here perhaps the most important disclosure control issue for a mathematical model is that if you have too many parameters in the model, if the number of parameters gets close to the number of observations, then that can become disclosive, because it's like deriving information on individuals. And so we only allow a model to have something like 30% of the number of observations in the data set. Okay, so first of all, does this work? I won't go into detail here, but here we're showing that if we use that method for fitting a generalized linear model, down the bottom left is what you get for a particular analysis here, in fact with 4 regression coefficients, using a conventionalized generalized linear model function in R. So you get a series of estimates and a series of standard errors. And these are then what you get in the Datashield analysis. And first of all, you can see they're very similar. And in fact, to take it further than that, they're more than similar, they're actually identical. And the only difference is because the number of significant figures we've carried. And so this is an important point. If you use this full likelihood approach, combining everything across all studies, and you use sufficient statistics, you will get exactly the same answer as you would if you had those data in a central warehouse. What about if you use study level meta-analysis? So at present, if you wanted, Nick, how much longer have I got?
Well, we've got 20 minutes, 1 minute, but maybe leave 10 minutes, 10 or 11 minutes.
Okay, right, great. So in study level meta-analysis, what the way, if, for example, if you look at most genetic association studies that are done by consortia of big genomic studies, what they do is they do these study level meta-analyses. Each analysis, the analysis center asks each study or data center to fit a particular set of models on their data, and then to send those results by email or phone or whatever they're going to do it by, so that those are then returned to the center. The center then, that study the request for those analyses is sent by email or phone. Each study does the analysis, creates its regression coefficients and standard errors, and returns those to the analysis center. And then the analysis center then combines those using some form of meta-analysis. Typically, it'll be a study level meta-analysis using often random effects meta-analysis. Now, this works fine and is a very good way of doing it. But if, for example, if you set off to do an analysis that was, you were wanting to look at associations between progression of a disease and, let's say, 1,000 blood markers, and you do this analysis and you find there are 50 significant hits in the data. So 1,000 of your markers do seem to be associated with the rate of disease progression. Now, the next thing that you might obviously want to do is look to see, does this effect of these markers vary with age or sex or ethnicity? So basically you want to look for effect modification by a series of variables. Now, you can only do those by fitting models with interactions. And unless you've originally asked the studies to fit those models with those interactions, you've now got to go back to them and ask them to fit it again with those interactions in. And because this is an administrative process, it can typically take days or weeks. And when you're working with genomics, where there's often a million parameters, if not a million things you're looking at, if not more, then you can see this is a very tedious process. The key point about Datashield is it allows exactly the same work to be carried out, but with complete central coordination by the analysis center, and it's all done in real time. So all that happens then, if you want to do SLMA in Datashield, is the analysis computer sends out a command, fit this generalized linear model on the data in each study to completion, return the results from that to the analysis computer. The analysis computer now does the study level meta-analysis. And now if we want to add interactions for effect modification, then it is as simple as basically, I realise that's not quite right. So it's as simple as changing a formula from the variable prog is to be related to a marker and the sex variable, to prog should be marker 17 times sex, and that will then fit the model with the interaction in it. So basically that again will be done in real time. So it literally takes seconds or minutes, not days or weeks. So just a bit more about the underlying architecture. So effectively there's two parts of the architecture. There's the client side, and there's a variety of architectures for the client side, of which the commonest is that I will be sitting here on a dumb terminal effectively, and I'll use that to attach to a client portal. And for a long time, our main client portal was in Groningen in the Netherlands, because the study that we were developing Datashield on was led from Groningen. And basically, when it gets that client portal, you basically log on to an R Studio there, which allows you to initiate R commands. Just to show these gears here are represent R environment. So this is the client side R environment. Each study then, if we now look at these, the remote data servers, first of all, their original data sits somewhere in their own data warehouse, which can be in any structure whatsoever. Then we've got this OPAL server, which is the Amoeba-based databasing system into which we embed this special version of R, such that the only way to get commands into R is through the parser that goes to the OPAL goes to the R server. And so so basically that's the setup of each of these studies. And so now see that I here can type in commands. The commands can get sent out to the OPAL servers, as we've already said. They allow data to be put into the R server and analysed in the way we've asked, and the analysis results, the summary statistics are then returned to the Datashield client portal, which we can then see. So basically under this particular structure allows us to do everything that I described earlier. And to be absolutely honest, the stats of Datashield are relatively straightforward once you understand them. But the development of this infrastructure was really spectacularly good, and I really have to thank my colleagues in Abiba who've done that and developed it further. Just recent developments are, first of all, rather than having to do this through the OPAL server, there's now a new system which allows another type of database called Armadillo, or Molgenis, which is part of Armadillo, and we're working to completely remove that restriction so that any database will be able to work. And the biggest change that's happened in the last year is that there's been a development of a thing called resources, which now mean that you can send a command into your R server here, which can then be passed on to obtain data from another site, for example, genomics data site, and then do that analysis, return the results back to the R server. So we can now, this allows us to do major big volume data, say genomics, without the actual values having to go into the OPAL server, which then makes it possible to do genomics. Now, Nick, would you like me to finish? Or, hang on.
No,
actually, I've got a few more slides. More slides?
Well, we should finish, I think, in 3 or 4 minutes to allow us to have...
Oh, yeah. So if we, okay, I'll just quickly whiz through this, all right? So, issues of disclosure control. First of all, you must never promise complete removal at the risk of disclosure. It always exists. Any effort you expend on disclosure control should balance the real risk of what would happen if a disclosure did occur and the real cost associated with trying to block it. So there's no one answer to say we've sorted out disclosure control. Secondly, the key reason for doing disclosure control is not to absolutely block the risk of disclosure, but it's to demonstrate to participants, data generators and data custodians that we are doing everything reasonable to try and reduce the risk of disclosure to an acceptable level, and in particular to be able to use the logging of the commands that are issued to enable us to identify clues in the analysis if someone does do something that allows data information to be released. And this then allows the potential post-op investigation of disclosure events, for example. Okay, I'll stop at that point.
Okay, well, that's great. So thank you. I found that particularly...
Shall I try and turn off my thing and appear myself?
Yes, that would be great. And anybody else who wants to show their face is welcome. So that's good, because Ian Thompson has put in the chat a question, and there he is in the bottom right-hand corner of my screen. So Ian, would you like to unmute yourself and ask your question?
Thank you, Nick, and thank you, Paul, for a very informative presentation. I'm particularly interested in this as I work in Scotland in the Digital Health and Care Directorate of the government, and we're busy looking at new ways of analysing GP data. So the question I have is really around the possibility of using this approach to link microdata from multiple different sources and yet only return the summary or aggregate statistics that you might have around that. You mentioned earlier in the presentation about this concept of vertical integration, and I think that's probably what I'm thinking about.
Okay, so first of all, in terms of horizontal partitioning, this is something there's a series of about 7 or 8 different studies that at the moment are talking to us about setting up Datashield, and one of those is Dundee, and that basically we're very keen I would really like to be able to apply Datashield in Scotland, because the information systems that you've got are so good historically that I think it would be really good. The second thing to say is that in fact, one of the main development projects under which Datashield was developed, and in particular the vertical partitioning bit of it, was the FAR Institute. So we were part of the FAR Institute Scotland and Wales, and so basically there's definite links with Scotland. The issue of vertical partitioning is that the reason why there's a difficulty with it, and it's not only in vertical partition, there's a series of other settings where you also have the same difficulty, is that at some point in the process of analysis you have to hold the data together on study from one source and another source. They've got to be held together somewhere at some point to do the analysis. And the way that you then, so unlike horizontal partitioning, where you can simply, because we can rely on the fact that the summary statistics are non-disclosive, in the case of the vertical one, you can't do that. So what you have to do is build encryption into it. And what we have done with it is develop a series. At the moment, it's very simple. We've got a series of approaches where you encrypt the data in each source and you pass it around in such a way that as a final step, you decrypt it somewhere where it's now safe. And basically, you can then do the analysis directly on it. So we have got ways to do that. One of the reasons, probably the primary reason why we haven't developed the vertical one any further, is simply because the horizontal one works so well and is so simple, and that's what most people are wanting. What we would really like to do is to get a use case, a vertical partitioning use case, and then develop it with a group that wants to do this because they want to be able to do the vertical partitioning. So that is something that we'd be very pleased to talk about further if that was possible. That answer your question?
That's great. Thank you very much.
Okay.
Okay, there's another question from Christopher Weatherburn, another Scottish fellow. So, Christopher, can you unmute and put your question to Paul? So if you are saying anything, you are muted, but I don't know. Is he muted, Shalane? I'll read out Christopher's question. Does that method work with increasing amounts of data as per challenge number 3, brackets big data?
Well, okay, so there's no reason why it shouldn't. And we are, in fact, again, a couple of the use cases that we're being presented with by some of the studies that we're looking to try and get funding with to do some work involve analysis of visual objects. So we're looking at ways, for example, that you'd be using neural net analysis of the figures of the diagrams, and then being able to do the analysis with that. In terms of how effective that will be, I can't really answer Chris's question on that, because until we do it, I don't know whether there's going to be any hidden problems. One of the good things to recognise about Datashield is that whenever we set Datashield up for any problem, immediately you can see there's a cost. If you've set up Datashield to analyse 10 studies, then clearly, because you've got to pass information backwards and forwards from the 10 studies, you can see that that's bound to slow things down somehow. However, there's also a gain, which is less obvious, which is that, in a sense, because the processing is all done at the study processing level, it means that you're parallelizing the main analysis. And what this means, and in fact, you can actually go further. The way things are going now, we're starting to look at using a high-performance computing already that's parallelized at different centers, so that you can really parallelize the thing down to a very low level. Now, that means that if you can do that, you can potentially speed things up. So one of the things that could happen with, for example, large data objects, which may be graphical, or they may, for example, be big genome scan results, is that if by keeping them in the places where they normally sit, you're just able to share the processing of those out more effectively across a number of sources. So that may well be helpful. So in summary, my answer to your question is that there's no reason why it shouldn't be possible. It should be able to be worked. We've not done it yet, so I can't be 100% certain, but you will then potentially get the benefit of the fact that you're sharing out the analysis across the centres.
Okay, thanks. Chris had said that his phone isn't unmuting, so it doesn't matter. We got a good response to that. There are no other questions on here. I've got one actually. I've heard through colleagues, Paul, that you've had a huge increase in the amount of interest in Datashield over the last year. And I was sort of forked question this. The first thing is, do you think that that was something to do with COVID? And secondly, is the work that Ben Goldacre is doing on Open Safely in Oxford with EMIS and TPP data centres in any way analogous to what you're doing, and what are the differences?
So first of all, in terms of the question about whether COVID was, it's an interesting question which I've not thought of before. The truth is, in fact, there have actually been, the application, the people who've approached us have actually been about COVID. So, and in fact, one of our major things at the moment is we're literally working with a group from Germany, waiting for a submission to an EU call to do some analysis precisely on that. So in that sense, COVID has done it. I don't think that the fact that we're sitting at home on Zoom all the time has affected anybody, but who knows? In terms of so Ben Goldacre Open Safely, so this is really important. There's a range of approaches that have been developed that have the same aim as Datashield, which is basically to be able to take data from multiple remote sources, analyze them where they are, and then bring the data centrally. Now, there's one big issue that discriminates the various methods. One of them, which is the Open Safely, is a great example of. Vantage 6 is another great example one, and a system called Viper. Basically, the aim of those ones is to allow systems to be in place such that you can do whatever analysis you would normally like to have done using whatever software you would like to have done. Instead of doing it locally, you're going to pass that to do it remotely. And the Vantage 6, which is associated with the personal health, has this idea of trains where you basically write algorithms that are getting shunted out to the studies, and then the results are being returned. Now, those systems are great, but what they don't have. So first of all, they're very convenient, and so they're really important as a complementary approach. What they don't have is they don't have any detailed disclosure control, and the reason for that is that every time we write a new function, we have to do a lot of work to develop the disclosure control for that each particular function. How detailed that has to be depends a bit on under what circumstance you want to apply it, but nevertheless it takes a lot of work to do that. So, for example, if in Open Safely or Vantage 6 you wanted to be able to set it up so that you could do an analysis with Stata or SPSS that had the same sort of disclosure controls, you would have to be working with the core source code of those programs. It would be a lot of work. So the way that we see it, and so we are in contact with Open Safely and with Vantage 6, we would really like to work with these guys as much as we can, because as we see it, Datashield provides a complementary solution. The disadvantage for Datashield is that ultimately all commands have to be written in R, and in fact they have to be written using the coding we use for client-side functions in R. So it basically, it's quite an acquired, there's a lot more people who can do it now, but it still takes quite a lot of work to learn to do it. So we don't have that convenience. On the other hand, we do have the fact that we can then offer this full disclosure. And so what we would like to see is a system like OpenSafely could be set up as it currently is, but then in addition, it could have a subset within it, where if you really want to do something that's got a disclosure control as well, then you can basically use that, just run that through the system. And we're talking already to Vantage 6 about doing that, and we've had slightly less discussion, but we hope to on OpenSafely on that. One other thing to say is that the issue of the fact you don't get disclosure control on one side, it makes it convenient because you can use your own software, and there's obviously no disclosure control. But what actually has to happen in most of these systems is it's not that there's no disclosure control. There has to be human disclosure control in the final step, so that you basically do analyses in whatever way you're going to do it, and then there's some human overview of the results that you're getting to make sure that you're not having to try to return something that could be disclosive. And this, for example, is also the centre of the UK Data Archive secure lab system. That basically, Datashield effectively allows you to get around, but you don't have to have that human step, which in some way, which not only speeds things up, but it also is less error prone in our view. And one of the things that we have thought and discussed with UK Data Archive, in fact, is the idea that you could use Datashield to provide a way to do analyses, first of all, when they're not absolutely supercritical. Secondly, it would allow you to do Datashield first, so leaving less human checking work to be done. And then if you wanted to do something that is sort of the equivalent of not releasing information about your security services or something, then obviously you do those only with human control. Does that answer?
Well, we're running out of time. That was a fantastic session, really informative. I really enjoyed it. I wonder if Paul would be happy to receive inquiries from people who want to know more, or possibly even collaborate. If we can liaise with Shalane, and Shalane can send out an email to those people who are interested. And finally, if you want to get your friends to watch this, it's published on our Faculty of Clinical Informatics YouTube channel, probably from sometime next week. I'm not sure about the exact timing, Shalane. Is it next week about right?
Great, that'd be brilliant. Fantastic. And Shalane, have you been in contact with Elaine Smith at my end, Shalane? Have you?
No.
Okay. Well, so she's the person to act. If people come to you and want to contact us, she's the conduit that you should go to. So I'll make sure that she contacts you.
Okay, that's great. Thank you.
Okay, so I missed what you said, Shalane, about when the YouTube channel version of this will be.
Yes, in a week's time. We will send an email out. Yeah, we'll send an email out just letting you know when that's up on the faculty website and YouTube channel.
Okay. Well, I'm pretty sure, Paul, that everybody's thoroughly enjoyed that. So thank you very much indeed. It was a great exposition about your project, and I'd really like to keep in touch. So thanks very much.
Thank you very much.